Saxon Algebra 2, lesson 69. Hey, remember those gas law problems we did a few lessons back, and we saw that for certain types of gases, whoops, that's a 1, sorry. You have the pressure and the volume divided by the temperature, and it has this way of balancing, of stabilizing itself, so that if you change any one of them, the others will adjust to stay in balance. That's why this is all, these are all 1s and these are all 2s, sorry. Let me just do this. There. We're going to go back to this problem. We're not going to change this formula at all. Make sure you memorize it. What we're going to do is simply use slightly more complicated values to plug in. It won't be bad, but yeah, I'll show you. There are only 2 examples in this lesson. So here comes the first one. Make sure, like I said, memorize this. If I show you a formula and put a puffy cloud around it, memorize it, okay? All right, so what we're gonna do is we're going to read the problem and we're gonna identify these. I'll read it through once just to let your head spin because it's really boring and it's got a bunch of crazy numbers in it. Then we'll fill in what we know and figure out which one we're supposed to find, all right? A quantity of an ideal gas had initial pressure, volume, and temperature values. Okay, so they go in that order. Pressure, volume, and temperature. Okay, it's the same as my list. Excuse me, I'm yawning, but I'm not bored. Okay, ready? 40 times 10 to the 4th atmospheres. I'm not gonna write down that unit. 40 times 10 to the 4th, good Lord. 0.0003 times 10 to the -6th is our volume. Oh wait, this is not an exponent. What am I doing? 0.0003 times 10 to the -6th. Scribble that out. That's just a regular 3. And the temperature is 700 times 10 to the 4th. Now you see what I mean about these numbers, right? They're all in scientific notation. Good Lord. Okay. Find the final temperature if the final pressure, I didn't put equal signs over here, if the final pressure was 0.0004 times 10 to the 15th atmospheres, and the final volume I don't know why I put a leading 0 on that one. It doesn't make any difference. You can or not, how you like. Okay, now you see how we've stepped up. Look at these numbers. They're disgusting. Right before we just had like 400 and 825. It was so much easier. These are these hideous values. I'm going to check them again just to be sure. Okay, this looks good. All right, so what we do, again, the process is quite simple. We plug these numbers into this, do algebra to solve for our missing variable, whichever one's not there. Now, I think I mentioned this when we did it before. I'm definitely going to mention it this time. Some people, including John and me, believe it's a good idea to first just solve this in the abstract for whichever variable you're looking for, and then plug in and simplify. That way you don't have to do algebra with these ridiculous, crazy numbers, right? So we're gonna take this original formula, P1 V1 over T1. Remember that if any of the 3 measures stays the same, that means we can drop it out of the calculation, We don't have that luxury here, but I just wanted to remind you of that. That if it ever says a certain thing holds steady or remains unchanged, something like that, we can just drop it straight out. Okay, so the first thing we want to do is solve for T2. So what I'm going to do is I'm going to cross multiply first. P1 V1 T2 equals P2 V2 T1. And then I'm looking for T2 by itself, so I'm going to divide away this other stuff. Now I have, this is all gone. Now I have a version of this same equation that is set up for T2, and I can just plug everything in. I'm going to do that on the top of the next page. Okay, that's just copying over what we did before. Okay, now I'm ready to set up some buckets and write in those crazy big numbers. And then we'll have to do some simplifying, won't we? All right. So let's see. P2 is 0.0004 times 10 to the 15th. I'm writing them in their crazy, ridiculous form, right? I'm not editing it all. V2 is okay, and T1 was 700 times 10 to the 4th. All right, I'm not doing anything to clean these up yet. Obviously, we'll have to do that later on. I'm just double checking to make sure I copied. It's so easy to make mistakes in this, right? That's an X. It's kind of hard to see. 0.015 times 10 to the minus 14, 700 times 10 to the 4th. Okay, great. Now I'm ready to fill in these. This is 40 times 10 to the 4th. And V1 is 0.0003. Okay, and I'm just double checking again. Double checking my copying skills here. All right, now we've plugged in the equation, which we rearranged for the variable we want, right? And now we've plugged in all the values. Now what we're going to do is we're going to go through and clean each one of these up and write it in proper scientific notation. All right? So this, let's start with this one. We need to move it 1, 2, 3, 4 times. So it becomes 4 times 10 to the negative 4, right? We'd make the number smaller to put it back in its original form, times 10 to the 15th. So that gives us, I'm going to write it down here, it's going to be my final, 4 times 10 to the 11th. You with me? Do you agree? Okay, that looks really almost like a fat one, but it's 11. Here. There, that looks better. Okay, now let's fix this one. We have to move it 1, 2 times, and we get 1.5 times 10 to the negative 2, and then times 10 to the minus 14. It's not 1.15, it's just 1.5. So this becomes 1.5 times 10 to the minus 16. Okay, this is just a work area. I'm not going to worry. I have to start this. Oh, this one's fine though, actually, so I don't need to fix it. 700, no, it's not. It would be 7 times 10 squared. We want this one to make it a number bigger, times 10 to the 4th. So that would be 7 times 10 to the 6th, right? So that's the 3 pieces of our numerator. This will all be T2. Okay, so those were the 3 pieces of our numerator in my workspace. I'm gonna draw the line there just so you can see. Okay, now we're going to the denominator. This one we have to move once. It's 4 times 10 to the 1st power times 10 to the 4th power. That will give us 4 times 10 to the 5th power. And then this one, 1, 2, 3, 4 jumps. 3 times 10 to the minus 4, because we want this 3 to get smaller. And then times 10 to the minus 6. So that becomes 3 times 10 to the minus 10. If you do not feel comfortable working with scientific notation, let me know and I will walk you through. Send me a problem that includes it and I will walk you through a simpler version of it. This is where we really use those skills and put them to work. We're not using calculators to do this. Eventually we'll use it in these problems, but these are still easy enough that we can do them with our own brains and we don't have to rely on a calculator. It makes it so much better. All right, so now we've got everything expressed in delightful scientific notation. So now we can simplify. First, we simplify the lead numbers. We remember we take them off and we're multiplying them all together. We can cancel and do whatever we want. So we have 4 times 1.5. Look, I just changed to it. I'm going to move it to an x. 1.5 times 7 over 4 times 3. Okay. Interesting. 4's cancel. 1.5 goes into 3 2 times, so I can cancel that and make this a 2. This gives me 7 over 2, and because this is a scientific-based problem, we'll change it to a decimal, 3.5. Beautiful. I like that this still is in proper scientific notation. You know how sometimes when you simplify all the lead coefficients, you'll get a number that has more than a ones place and you have to adjust it back again. It's so annoying. This one behaved itself and stayed right there. Now we're going to use the product rule and the quotient rule to simplify all the exponents on the tens, right? Product rule says that if we're multiplying the bases, we add them. So we're going to add all of these. Will be 11. I'm going to scoot this up a little so you can see better. 11 plus minus 16 plus 6 minus the 5. We subtract what's in the bottom minus a minus 10. Okay? I used buckets anywhere I thought they might help me keep straight what's going on. All right, you can toss them in anywhere you think there's a potential for confusion, and believe me, there's potential for confusion here. All right, this becomes a positive. I'm going to add together all my positive numbers first. 11 plus 6 is 17, plus 10 more is 27. Then I'm going to write all my negative numbers. 16 minus 5, negative 16 minus 5 is negative 21. And that gives me an ending power of 6. That means my final answer, I use this and this, my final answer is 3.5 times 10 to the 6th. And that is our value for T2, and T stands for temperature, and temperature is measured in kelvins, so I write the abbreviation for that at the end. I don't have to know that. I just look in the book to remind me what's the unit on this variable. Did I get it right? 3.5 times 10 to the 6th K. Yay, this is the right answer. Remember that when we're simplifying these lead coefficients, it's super important that we get this number adjusted so it only has a unit in the ones place. Got it? Okay, good. Let's do one more of these. Example 69.2. All right, I'm going to start by listing the variables I expect to see. And up here, I'm going to write our formula in its general form. And then we'll adjust it after we figure out which one's missing. Ready? A quantity of ideal gas had initial values of 0.003 times 10 to the 14th pounds per inch. That's a pressure. 0.007 centimeters cubed. That's a volume. And 7,000 K. Oh, I don't need to write the unit. I'll just put it though, so it doesn't look like a 1. Okay, those are our initials. John writes them in order, but if we get confused at all, we can look at the units and trace them back in the original problem, in the original lesson where we learned about gas law problems. There was a list that said the different kinds of units that could be used to measure pressure, volume, and temperature. That's what's tricky is for pressure and volume. You can measure it in multiple ways. So if you ever need to look back at that, just look in the glossary for the ideal gas law lesson and jump into it and find that list. P2. Find P2, okay, that's what we're looking for. If the final volume was 3 times 10 to the 3rd, no, 3 times 10 squared, and the final temperature was that. Solve the equation for P2 as the first step. Yeah, that's what we want to do. We want to rearrange this thing. So what I'm going to do, I'm not going to rewrite it just as it is. I'm going to cross multiply. For my first step, P1 V1 T2 equals P2 V2 T1. I'm looking for this, so I'll divide by the other 2. This all cancels, and then I'll write it over here. This is the form of the equation I want to use for this problem, right? So I'll write P2 equals, and then I'll put 3 on the top, 2 on the bottom, because we have 3 letters on the top and 2 on the bottom. All right, now I'm ready to plug in P1. Bucket was too small. I'm going overboard, okay? V1. I'm gonna double check that one, make sure I copied it right. Good, okay. And then the other number that goes on the top is T2, which is over here. Okay, and I'm just checking to make sure I copied all of that correctly. It's so easy to make a mistake in this. 10 to the 14th, 007. Okay, good. And now in the denominator, I put in V2, 3 times 10 squared, and T1, which is just straight 7,000. Well, the denominator looks kind of cute, right? All right, now we've got all the values where we want them. As John would say, we've inserted the numbers, and now we need to clean it up. So the first thing we're going to do is express each of these beasts in proper scientific notation. This little guy wins the award. He's already there, but I'm going to give myself a little workspace, and then down here, I'm going to write the final form of this, all right? This needs to move 1, 2, 3 times, so that would be 3 times 10 to the minus 3, and then times 10 to the 14th. And that is 3 times 10 to the 11th. This is my final, this is my workspace, and this is my final form of the fraction. All right, this one just has to go 1, 2, 3, so that's 7 times 10 to the minus 3. Okay, I don't really need a workspace for that one. And then this one, 1, 2, 3, 3 times 10 to the minus 3 times 10 to the 7th will give me 3 times 10 to the 4th. All right, I feel good about that. That's the numerator. The denominator is much easier in this one. This is exactly perfect as it is, and this one's really easy to do in my head. 7 times 10 to the 1, 2, 3. Okay, beautiful. Now, you know what I'm gonna do? Oh, well. I hate to copy it, but I don't want to squish it either. So I'm going to take 3 times 7 times 3 divided by 3 times 7. I'm going to write that at the top of the next page. That's me summarizing all these lead coefficients and then getting ready to simplify. 3 times 7 times 3 over 3 times 7. Well, that's not going to be too hard to cancel, is it? Goodbye, goodbye. Our new coefficient, significant digit, is 3. Beautiful. Now I'm going to turn to my numbers. I'm going to add these 3, and then I'm going to subtract those 3. All right? So it is, the first one was 11 plus a minus 3 plus a 4. 11 minus 3 and a 4. And now I'm going to subtract 2 and subtract 3. Minus 2 minus 3. Remember, what I'm doing here is I'm using the product and quotient rules to simplify all of those exponents because they're all on 10, so all their bases match. So I can just scrunch them all together. And this gives me, I'm going to do positives are 15 minus all the negatives are 8, and that gives me a 7. So my final answer for P2 equals 3 times 10 to the 7th. I do not have any adjustment I have to make, but I always double check that to make sure that my ending value just has the one significant digit and anything else is pushed to the decimals. As you can see, oh, I forgot a unit. Pounds per square inch. As you can see, even though these numbers are crazy, we don't need a calculator. We can just use our scientific notation skills to simplify. Later, I'm just going to give you spoilers. Later, we're going to do numbers so complicated that we will need our calculators to solve them. But today is not that day, said Aragorn. Today is the day that we can still do these in our heads. All right, that is lesson 69. Look at what you can do. I hope you feel smart. I hope you feel really, really smart. And know that if you take the chemistry class that requires this calculation, you're going to kill it. And all of your classmates are going to turn and look at you and go, how do you know how to do that? And you're going to say, thanks, John. And so will I. Thank you, bye.